Institute of Engineering and Technology.
Hello students, in the discussion of matrix algebra, now we are at our third main part of applications of matrix algebra. From this particular section, we are moving from calculation of properties of matrices towards applications of matrices. All of us know that how to find intersections of two lines. If I will give you two equations, linear equations, and if I'll ask you that find intersection of those two linear equations in form of line. Obviously, whenever you are finding intersection of two lines, they can generate three possible solutions. They can intersect into a single point. They can be a same line at all, that means they can give you infinitely many solutions. And third possible case is parallel lines. Means it may happen that your lines are remaining parallel to each other, they will never intersect to each other. But now, if I want to generalize the same idea or the same concept of intersection for three planes in three-dimensional space, how we can find that particular solution? For example, if I ask you that if you have three different planes, tell me how many possible solutions are there in form of intersection. You should pause at this particular part, you should think over it, and then again come back. I will give you answer after this small pause. Quite tricky. Whenever you will go for the visualization of this thing, that how we can find intersection of three planes, it is comparatively difficult than finding intersection of two lines. Let me discuss various possible solutions of intersections of planes. Starting from no intersection, means you have three different planes remaining as a layers parallel to each other. That means they are not intersecting at all. So now you have no solution. So this is the first category of the solution, which means inconsistency in form of solution. Let us discuss another part. Suppose you have a plane and another plane is intersecting perpendicularly exactly at some point. So now intersection of two planes is a line. So now we can say that these two planes are intersecting to each other on a line, and then if your third plane is again intersecting it in such a way that it is perpendicular to the line of intersection of two previous planes. Like all of us know how we are considering walls in particular room. If I consider a left-handed wall, a right-handed wall, and the floor, these three will be working as a plane. And then you can see the corner point is nothing but common intersection. We are always interested in that common intersection of planes. So in this case, they are intersecting in a single point. So we can say that solution is a unique point. We can say origin in form of XYZ space. Now, is there any another possibility of the solution? The answer is yes. As I told you that if you have a plane and another plane which is perpendicularly intersecting to that, then intersection is a line. Now suppose there is a third plane passing through that line of intersection of previous two planes, then you can say now the intersection of three different planes is a line. So that means now there are infinitely many points which will work as a point of intersection of these three planes. So there is another category of solution also. Is there any another possibility? Again, answer is yes. Suppose you have three planes lying on each other, that means they represent the same plane. all three planes, they are actually merged to a single plane. Then points on that plane, they are solution. So ultimately what I want to discuss in this part is, if you move from 2D to 3D, the linear structures itself, they are working in a complex manner. And then today we are going to discuss how to figure out that intersection, whether they are intersecting in a single point, on a line, or on plane. Or the third category, that means no solution, whether they are remaining parallel to each other or not. We'll develop a mathematical method. In fact, we'll give you two methods to find this particular question's answer using matrix algebra. And this is the one of the most applicable part of matrix algebra. So let us start this thing, that is in matrix algebra known as system of linear equations. System means we are taking simultaneously more than two equations, and linear means there are no curvature into the structure. They are flat, like straight line, like planes. Now let us consider this technique of system of linear equations. We have two different possibilities of linear equations. One is homogeneous system, another is non-homogeneous system. Homogeneous system means on the right hand side of the equation your all entries are 0. But if at least one entry is there with non-zero values on the right hand side, that system is known as non-homogeneous system. So to consider this technique, I am considering three equations at a time. Later on we'll see how to generalize this up to n equations with n unknown. This is 3 cross 3 system, 3 equations, 3 unknowns. So here x, y, z, they are unknowns. A11, A22, A33 up to A33, they are coefficients, and B1, B2, B3, they are the constants on the right hand side. The first and the foremost step would be to convert this into the matrix form. I will consider capital A as the coefficients of x, y, z in equation set. I will take column vector capital X as column of unknowns x, y, z, and I will take column vector B as column of constants on the right hand side. So if I take these three matrices A, X and B, now my next step is to consider augmentation of two matrices A and B. You already know how to go for the augmentation. I already discussed this thing in my previous video in method of Jordan's inverse. So now I will merge matrix A and matrix B, something like this. And now my focus is on rank of this matrix A. So what I will do to find rank, we know that if we convert matrix A into row echelon form, then total number of pivots will give me rank of the matrix. So for that, I am converting this matrix A into row echelon form. I am not worried about that another part on the right hand side. My focus would be always on the part in orange color, means in A. Suppose this is the row echelon form of the matrix. A11, A22, A33, they are the pivots. So now I can say that I can find rank of matrix A as well as I can find rank of matrix A augmented B also. The augmentation will help you to find separately rank of a submatrix as well as the whole matrix at a time. The next calculation in our consideration would be this. After converting matrix into row echelon form, now we can check whether our system is consistent or not. Consistent system means whether planes represented by these three equations, they are intersecting or not. So condition is like this: if rank of A and rank of A augmented B, they are remaining same, then and then only system is consistent. Then once we have the surety of consistency, means this technique or this condition will give you only surety of the consistency, means they are intersecting. Still we don't know whether they are intersecting in a point, whether they are intersecting on a line, or whether they are intersecting on a plane. For that we have two different methods of calculation. Up to this step, necessary condition of consistency, our calculation will remain same. Take A augmented B, convert A into row echelon form, find rank of A and rank of A augmented B. Once you have the surety, means the consistency, find the point of intersection. If your system is inconsistent at this step, your process will end. No need to go for any method, because these methods are to find ultimately intersections of the planes or solution of the system. Two methods are there. The first method is known as Gauss elimination method. And for that, what we'll do, at the end of our consistency step, we have the row echelon form of A augmented B. At this particular part, what we'll do, we'll convert again this matrix into equations. Something like this. See, we have augmented matrix into the row echelon form, and then we'll transform it into equations. And then the second and the foremost interesting step at this stage is back substitution. We'll select the bottommost equation, A33z equal to B3, we'll find value of z from that, and that is B3 upon A33. We'll plug in that value into upper equation, so value of y will be eliminated. This is how we are eliminating variable by variable using back substitution. So it is known as Gauss elimination method. Two steps. Convert matrix A augmented B into row echelon form, check consistency, go for the equation system again, and then go for the back substitution. So at the end of this, you will get values of x, y, z. Now let us focus on another method. The second method is, after this Gauss elimination, it is known as Gauss-Jordan method. Now what is difference in between Gauss elimination and Gauss-Jordan method? In Gauss-Jordan method, we are not directly converting our matrix into equations, but we are focusing on the same matrix and we are further reducing it into reduced row echelon form. So your matrix will look something like this. Now it is in a reduced row echelon form. So clearly now, whenever you will convert this into equations, finally it will give you answer of x, y, z easily. So the technique is almost the same. In Gauss elimination method, you are converting it into equation and solving equation. Whereas here in Gauss-Jordan method, you are remaining in the matrix only, you are further converting it into reduced row echelon form. So now no need to go for back substitution, as it gives you directly value of x, y, z. So it depends on the selection of method. You can select any method, ultimately your answer will be same. Now let us discuss types of solution. As we know that there are three possibilities. There can be no solution, means inconsistency. There can be consistency in a single point, means unique solution. And there can be infinitely many solutions. In case of plane, they are on line or they can be on plane. But we are collectively considering all those infinitely many intersections in third part, which is infinitely many solutions of system. So we'll divide this solution into three parts. Now see here, the first condition is for consistency that rank of A and rank of A augmented B are same. We are denoting it by R. And we are also denoting the number of variables included into the system. In our case, it is x, y, z. I am denoting it by n. So n indicates total number of variables or unknowns into the system. And R indicates common rank of A augmented B. Let us go for the first case. When we can say that system is with unique solution. If this value of R is exactly equal to n, then system is consistent with unique solution. At the rank of the matrix, see, whenever you are finding necessary condition of the consistency of the matrix, you can directly check whether one of these three is satisfied or not. And then you can select the method of Gauss-Jordan and Gauss elimination. Second case, infinitely many solutions. In that case, what will happen? R will be less than n. Rank of the matrix will be less than n, means total number of variables included into the system. This will generate infinitely many solutions. Now what do we mean by infinitely many solutions? Infinitely many solutions means A solution is one dimensional, two dimensional, or n minus one dimensional. To find the dimension, we need free variables. As I told you that if you have three planes intersecting in the same line, that is one dimensional solutions, means you can move freely in 1D. So for that you need one free variable. If your three planes are sticking to each other, that means intersection can move freely in two-dimensional part. And so it is two-dimensional solution. So for that we need two free variables. This is the logic of finding free variables. Now once you have R and N, and if R is less than N, number of free variables are always N minus R. Suppose this N minus R for our 3x3 system is 1, that means planes are intersecting in a straight line. If value of T means free variable is 2, that means 3 planes are sticking on each other. I hope this part is clear. Okay, now let us move to the third part. If R is not equal to N, system is inconsistent. Means planes are remaining parallel to each other, lines are remaining parallel to each other. I hope this part of types of solution is clear now. Okay, and to find this answer of unique solution or infinitely many solution, you can go for Gauss-Jordan method, you can go for Gauss elimination method. Now we are going to discuss examples for all these three possible solutions. So first example is find solution of this system. Now my first step is to convert this into matrix form. So here you can see clearly I am collecting all coefficients of x, y, z into a matrix which is A. I am collecting x, y, z into column which is capital X, and I am collecting 1 to 1 which is capital B. Taking augmented matrix A with B. Focus on A, convert it into row echelon form. No need to convert it into reduced row echelon form at a moment. Convert only this matrix into row echelon form. So I am selecting first row, entry is 1, lower entries are 2 and 3. So multiply 1 with minus 2, add it into second. Multiply 1 with minus 3, add it into 3. And then once you have that row, fixed row 1, move to the second row 2. Now it is minus 3 and lower entry is also minus 3. Just simply take subtraction. So lower entries are now 0. Now at this point in this matrix, you can observe one thing very clearly. If you hide that part on the left hand side, which is column 1, 0, 2, the part which remains is only A. So rank of A is 2 because there are only 2 non-zero rows in A part. But if I consider the whole matrix A augmented B, there are 3 non-zero rows. Pivots are 1, minus 3 and minus 2. So at this moment, I can say clearly that rank of A, only A is 2 and A augmented B is 3. So rank of A is not equal to A augmented B, and therefore the system is inconsistent. So remember one thing, if your pivot is shifted into B part, system will be inconsistent. Your pivot must remain inside part A throughout the row operations. So this is the first case where your equations are not intersecting. That means now I can say that the three equations which were representing planes, they are not intersecting, they are remaining parallel to each other. Or I can say another possibility is they are intersecting, but they are not intersecting in a common point. So I hope this first part is clear. No solution or inconsistency. Now let us go for the second. Suppose this is the system, again convert it into matrix form, take A augmented B, find its row echelon form, again 1, 2, 3. See, I am just changing values on the right hand side. The left handed values are remaining almost same. So I am now converting this matrix into row echelon form. First pivot entry of the first row is 1, converting lower entries into 0, multiply 1 with minus 2, add into 2, multiply 1 with minus 3, add into 3. So now my pivot is 1, lower entries are 0. Now coming to the second pivot. Second row is multiplication of 5. So now you can divide throughout by 5. I am dividing it by minus 5. Again, third row is all multiples of 2. I am dividing throughout by minus 2. So it will convert your pivots into 1. calculation will be comparatively easy. Now, if I take R3 minus R2, my lower entry of second pivot is 0. So that means now we are almost done with this, and then you can divide your third row with minus 4. So now you have all 3 pivots present in part A, and that means rank of A is 3, rank of A augmented B is also 3. See, this is the thing which will ensure you about the consistency. Therefore, rank of A equal to rank of A augmented B is 3. We are denoting it by R. Number of variables denoted by n, which is equal to 3. These are nothing but x, y and z. Number of unknowns into the equation. So now we can say that system is consistent because rank of A, rank of A augmented B are same, and it is consistent with unique solution as n is equal to R. So now we can select any one method, Jordan or elimination, to find this unique point of intersection. So let us select Gauss-Jordan method. In this method, what we are doing, we are converting this row echelon form of A further into reduced row echelon form. So selecting the bottommost pivot, which is A331, converting upper entries into 0. So I am taking R1 plus 2R3, R2 plus R3, and then focusing on second pivot A22 position, converting upper entry into 0. So this gives me solution x equal to 0, y equal to 3, z equal to 1. So these coordinates are coordinates of point in 3-dimensional space where all of your 3 planes are going to intersect. So I hope this second part is also clear, how to find Gauss, how to apply Gauss-Jordan's method to find point of intersection. You can also go for Gauss elimination method. It will give you same answer, 0, 3 and 1. Now let us consider third case. Suppose this is the given system, convert it into A, X and P form, take augmented matrix A with P, convert matrix A into row echelon form, multiply 1 by minus 2, add it into 2, multiply 1 by minus 4, add it into 3. Now surprisingly, at this particular moment, we have 2 same rows. So what I will do, I will take R3 minus R2. So lower entry is 0 in third row. And then I am taking R3 minus R2. So now you can see clearly at this junction that rank of A and rank of A augmented B both are same, and both are equal to 2. So value of R is 2, but number of unknowns, which is n, is equal to 3. So n greater than R means system is with infinitely many solutions. As I told you that whenever you have value of n which is bigger than R, it will give you infinitely many solutions. Once we have infinitely many solutions, our next thing would be how to find how many free variables are there. And for that we are taking t, which is n minus R. So this simply means that value of t free variables is equal to 1. That means my 3 given planes are intersecting in a one free dimensional result, that is a line. Your planes are intersecting in a line. Now to find that line, I am considering this method, which is Gauss elimination method. Now we convert this system into equation. That was our first step in elimination method. And then it gives me x plus y minus 2z equal to 1, y minus z equal to 2. We have freedom to select one variable as a free variable, as t is equal to 1. So always select the last variable as a free variable. So I am selecting z, although you can select y also. We need to select variables which are common in these two equations. I am selecting z. Suppose z is equal to t. So from the last equation, y is equal to 2 plus z, so y is 2 plus t. Value of x, 1 minus 2 plus t plus 2t. So ultimately I will get this parametric form of line, x equal to minus 1 plus 3d, y equal to 2 plus t, z equal to t. This is how I can find infinitely many solutions with one free variable, means I can move in 1D, so all 3 planes are intersecting on a line. I hope all of you understand now this technique of finding solution of 3 equations. You can generalize this for n equations also. 2 steps. Check whether consistency is there or not and then select the method of Jordan or elimination. Thank you.
LJ Institute of Engineering and Technology.